So there's already a video, classroom video of this section 6.6 application of linear models. But there's a couple things I want to add. One is there's a little bit of confusion about some of the notation. And the second is I'll work through the actual example because I think the example doesn't get worked out on the classroom video. So just in this scheme of things here that we're looking at, just realize that the x1, y1, x2, y2, x3, y3, those are given points, right? But the beta 0 plus beta 1x, beta 0 plus beta 1x2, beta 0 plus beta 1x3, those y coordinates are sort of like what we're trying to find, right? They would be y coordinates on the line that best fits. So beta 0 and beta 1 are the unknowns here, and yet beta 0 plus beta 1x, etc., are y coordinates on the line that best fits. So if I were to write, let's move this up a bit, this column vector beta 0 plus beta 1 x1, beta 0 plus beta 1 x2. The only thing that's changing here is the x coordinate, beta 0 plus beta 1 xn, I would say, is my last one. So this is a column vector of y coordinates on the actual line that best fits the data, right? Probably different from the y coordinates that were given. What we want to do is we just want to express this in terms of matrix multiplication. We want to think of it as a matrix times the column vector beta 0, beta 1. And if I think of these coefficients of beta 0 as 1, all the way down the line, then of course I can just think of this guy as beta 0 times 1, 1, 1, all the way down the line 1, these are all 1s, plus beta 1 times a column vector with entries x1, x2, x3 onto xn. And so working my way backwards through matrix multiplication, I can just make the 1s first column, the x1, x2, x3 to xn, the second column of matrix times the column vector beta 0, beta 1, that will give me this guy, okay? So I know the 1s seem kind of mysterious on the next page to some people, like why did I make this matrix of 1s? Those 1s are just the coefficients of beta 0, which is the y-intercept value of the linear equation. Beta 1 is the slope value, okay? So we're trying to solve a system of the form ax equals b, but for whatever reason our textbook is using different notation here. And so we're writing capital X in terms of a. We're writing the beta column vector. That's really our variable. And then the y column vector, the column vector of y coordinates, so just y1, y2 to yn. That's what we would want the x beta, this is x beta right here. The x beta column vector we want equal to the y column vector, but it's not normally going to come out to be equal, and there's no solution beta 0, beta 1 that makes them equal. So we apply the least squares process, and we end up taking x transpose x beta equals x transpose y, and we want to solve this system for beta, which is just beta 0, beta 1, which are the y-intercept and slope of the line that best fits the data. So let's go ahead and do the exercise now. And so I'm kind of a simple example. Of course, a more meaningful example would have many, many, many more data points, but I'm sure this gets the gist of the thing across to us. So we have just these 4 points, 1, 3, 2, 1, 3, 0, 4, negative 4, and we're trying to find beta 0 and beta 1 of the line that best fits the data. So my X matrix is going to have 1s in the first column, X coordinates in the second column. So 1, 2, 3, 4. 1, 2, 3, 4 is the second column. No matter what the situation, the first column is 1, 1, 1, 1. Again, they correspond to 1 being the coefficient of the beta 0 y-intercept term. And, of course, beta is beta 0, beta 1. And my y vector here will be 3, 1, 0, negative 4 of y coordinates. I need to calculate x transpose times x, which is going to be 1, 1, 1, 1, 1, 2, 3, 4 times 1, 1, 1, 1, 1, 2, 3, 4, like so. So I'm taking 2 by 4 matrix times a 4 by 2 matrix, so I should get a 2 by 2, right? 1, 2, 3, 4, I think I get. Going across the first row here and second column here, I get 1 plus 2 plus 3 plus 4, that's 10. And going across the second row here, first column, 1 plus 2 plus 3 plus 4 is 10. And then second row, second column, I get 1 squared plus 2 squared plus 3 squared plus 4 squared. Those are the squares in the least squared method. So that's 1 plus 4 plus 9 plus 16 is going to be 30. Now I also need X transpose Y, which is 1, 1, 1, 2, 1, 3, 1, 4 times 3, 1, 0, negative 4. And X transpose Y will just be a 2 by 1 column vector, and 3 plus 1 plus 0 plus negative 4, I get 0 in the first entry, and then I get 3 plus 2 is 5 plus 0, 5 minus 16, negative 11. Okay. So we want to solve 4, 10, 10, 30 times beta 0, beta 1 equals 0, negative 11. Okay. That system. So my augmented matrix is 4, 10, 10, 30, 0, negative 11. And when I reduce that, I got to, let's see, I have 1, 2.5, 0, 1, 0, negative 2.2. So that's not in reduced form. Let's go all the way to reduced form. So add negative 2.5 times row 2 to row 1. So I'm going to get 1, 0, and now what do I get? 2.2 times 2.5. And I'm going to add a negative this to this. So I believe I'm going to get 5.5. And then I have 0, 1, negative 2.2. Okay. So it turns out here there's a unique solution. So beta 0 is equal to 5.5, beta 1 is equal to negative 2.2. And so that means my line is 5.5 minus 2.2x. I mean, we're used to writing that in the reverse direction, right? I'm just following the book's convention. 5.5 is the y-intercept, and negative 2.2 is the slope of a line. So that's the answer. And just for for fun, I graphed the line with the 4 points. This is 1, 3, 2, 1, 3, 0, and what is it? 4. What was the other one? 4, negative 4. And along with, I very carefully graphed the line with the negative 2.2 slope and 5.5 y-intercept. So there it is. But I like this application. It's a pretty cool way to actually show how we obtain this line of best fit for those given data points. And that's it.